Okay, so let's work on this problem that has a non-conventional boundary condition. In fact, as you can see, this beam is not fixed to the wall on the left, and it has two conditions. One, it's a roller right here. It's a pin. Let's put some labels here: A, B, C, and it's roller at point C. And we want to find, for example, deflection for this beam, deflection of neutral axis. So before I do that, the first thing I do, I want to find the reactions at point A and C. So the first thing I do, I take the entire thing as system and go ahead and draw a PD for that. So that's the beam. One right here. You have AX, AY. Well, we can just ignore AX because there is nothing in the X. Right here, 1 Newton meter couple, CY, and 2 right here. And also let's put some length here. Again, simplifying 1, 1, 1, 1. These are all the length that we need to find our unknowns here. Well, obviously AX is 0, so I write moment about point A, 0. That's going to give me CY, so I get 1 plus is come from this. Well, I'm not going to mark it because you know this stuff pretty well, so I'm not going to repeat things from vector statics. So 1 plus, and then you have a -1 couple moment right there, plus CY times 2 minus 2 times 1, 2, 3 is equal to 0. And then I can write summation of moment about point C is equal to 0 to get AY. You could also, instead of doing two moment equations, you could just do one moment equation and one summation of force in Y direction 0. Either way, whatever you're more comfortable, do that. So if I do moment about C, then I get -2, -1, negative AY times 2 plus 1 times 1, 2, 3 is equal to 0. So let's solve these two equations. The first one, let's pick a different color here, is cancelled out with this. Then CY is simply 3. Okay, CY, let's write it here. CY is equal to 3. And right here you have -3, and here +3 right here. That means AY is equal to this cancel out with this, and then AY is 0. Okay, so in fact what I get is, let's draw this beam one more time, is a beam under this kind of loading. I want to use another color to put the loadings to be more visible. One here. At A I have nothing, so I don't put anything at A. Then at B I have 1 Newton meter. At C I have a CY, which is upward and is equal to 3, and then there is 2 and the other end. Interestingly, AY is 0. If we, for example, if we had something like AY is equal to 2, we could just put another 2 here. And you really don't worry about how many forces you have. As long as you use heavy side, your job is pretty simple. You will end up with just one line equation for moment relation, right? So it really doesn't matter if the AY is non-zero, but accidentally it became 0 here. So I don't put any AY right here. So this is my free body diagram for this problem. So the next step is to find the moment relation. Why? Because or the moment diagram, because what I want to do, I want to replace it in this equation. The second derivative of deflection is equal to m over ei. So for this to be integrated, I need to have mx. So that's the reason I need to find moment relation. So in order to do that, again, you need to take a reference from either left or right. I like to take my reference from left, and then you cut it from the very end, but you know that not exactly the end. You take it the very end point that includes all the loading starting from 0 to x. And here, this distance, let's call this x. And I know that I just work with the left part of the beam. The right part is not my system. So I just go ahead and draw FVD for my system in this case. Let's get this black back again here. Erase this equation. We don't need it right now. All right. So for that, this is my system. 1 right here, 1, 3, and there's going to be mx and v of x going down, and that's all I get. And don't forget, this point starting from here to here, this distance is x. Other distances, I want to pick another color for distance. I wish I could draw this distance with also green. Alright, so pick the green pen. From here to here is x, and then from here to here is 2, from here to here is 1, and from here to here is also 1, and that's all. Sorry, from here to here is not 1. So this one is x, this is correct. Okay, from point A, from the beginning to point A is 1, and then from A to B is 1, so the total 2 right here is correct. And then from point B to C is 1, and then from point C to the point that we cut, we can simply say it's heavy side x minus 3. I'm talking about this distance. This is not 1 because we are not cutting at the very end point. Okay, so this distance you have to find it versus x. So I'll put a question mark here. Okay, so write the equation, summation of moment about point x is equal to 0, and then I start finding the moment and add them up together. Okay, so the first one is positive mx, obviously. The moment coming from vx is 0. Then you go to the 3. The moment coming from 3 is 3 times moment arm, which is heavy side, x minus 3. Positive or negative, if you take your right hand, then you can quickly see this is negative. The next one is a couple moment. The car movement doesn't need a moment arm, but it needs a switch to make it on or off. So you say 1 times heavy side x minus 2 power 0, and because its sign is negative, you put a negative here. Okay, we already mentioned why we say x minus 2 to the power 0 in the previous video. And then you go and find the moment coming from this force. Let's highlight it, the very end one, with respect to point x right here. Obviously that moment is equal to 1, the value of force times moment arm, which is x. Look, I don't need to use Heaviside function because that force, regardless of where my x is, that force is always included. So I don't need to put a switch on it, right? So 1 times x, and the value is positive. So this is all the moment I have on the beam. They must be, the sum of all moments should be 0. So that's going to give me an equation for mx. So I can write mx is equal to, solve it for mx, is equal to 3x minus 3 plus heavy side x minus 2 to 0 minus x. This relation. So I may ask you to draw this maybe in the final exam, and you know how to draw it. You take 3 intervals, 1 x from, so the way you do that, you say 1 x between 0 and 2, and in that case your function is simply, let's use a different color, you don't have the first term, you don't have the second term, and your function, your moment relation is simply the last term, negative x. The other case, when x is between 2 and 3, okay, then your mx is equal to, let's go back here, x is between 2 and 3. So you don't have this first term, because your x must be greater than 3 in order to get that term. So this term is just simply doesn't exist, it's a null. The second term, do you have it, yes or no? Then you say, well, my x is greater than 2. So I do have, this reduces to heavy side reduces to x minus 2 inside parentheses, because x is greater than 2. It becomes itself whatever is inside Heaviside function, right? And x minus 2 to power 0 is 1. So your relation becomes 1 minus x. 1 minus x when x is between 2 and 3. Now let's go between 3 and 4. So this is the very last part of the beam. In this case, you have all the terms. So your mx is equal to, the first term gives you 3 times parentheses x minus 3. So let's write here 3 times parentheses x minus 3. The second term again give you 1 plus 1, and the last term right here is still negative x. Note that we always have that negative x in the equation. Okay, so this, if you simplify, 3x minus x is 2x, and then negative 9 plus 1 is negative 8. So this is the relation. So all you do, you plot these 3 relations, which is basically, if I want to plot it right here on the beam, first you have a negative x, and then you have at point 2, if put x is equal to 2, then you get this goes right here, and you have something like this again, and then the slope become positive, and you go like this. So that's going to give you a moment relation. So you have a jump right here. Okay, so anyway, let's go back to the calculation of deflection. So all I do, I solve this equation. The second derivative of v with respect to x is equal to m over ei. Once again, we assume that ei is 1. And you simply have the second derivative, let's show it with dot, makes it quicker, faster, and simpler, is equal to m of x. We need to solve this differential equation. But what are the boundary conditions? The boundary condition is the deflection at point x is equal to 1. Let's go back to the original beam. Look at here. At point ax, I want to zoom and highlight it. There is no way that this beam can go down. If this beam, for example, or up, if this beam is going to deflect like that, okay, arbitrary deflection, those 2 points at A and C are always fixed. There is no way that this beam at point A and C can go down. You can see that. So the deflection at point A and C is equal to 0. So let's write it here. These are the boundary conditions for solving this differential equation. So V at point A, V deflection of point A is equal to 0. Deflection of point C is also 0. How many conditions do I have? 2. How many constant of integration do I get from this second derivative? Well, if I double integrate, I get 2 constant of integration. I have 2 conditions right here. Then I can fully determine the curve for the deflection, right? So let's do that. What is the x of point A? You see, I want to write this in terms of x. What is the x location of point A? The point A is located, let's zoom here, is located from the left side. This x is equal to 1. So here, this relation, instead of v of A is equal to 0, I can write v at x is equal to 1 is equal to 0. This is more practical. When I want to set the x to something, I use this relation. The other one is v at x is equal to, what is the x of point C? Going back to this plot right here, the x of point C is from the left is 1, 2, 3. So v, the other condition is v at point x is equal to 3 is equal to 0. So let's go ahead and solve this differential equation by double integration and apply these 2 conditions. One, let's label them condition 1, condition 2. So if I integrate that, I get the first thing I get. Let's plug mx. So you have the second derivative is equal to m of x, which I use this relation. So plug it right here. So you get 3 times x minus 3 inside heavy side plus heavy side x minus 2 to 0 minus x. So this is my equation, ordinary differential equation, that I have to double integrate and solve. The first integration, if you integrate both sides, you get v dot is equal to 3x minus 3 to 2 over 2. And we already discussed that how to integrate a Heaviside function. Well, just treat it like a derivative, like a parenthesis when you take integral. It's like you are taking integral of x minus 3 inside parentheses. What do? Go back to your calculus book. You do x minus 3 second power divided by 2. If you don't believe it, take derivative of that, and then with respect to x, and then you come back to this. Integral is sometimes called antiderivative. Okay, so their operation is opposite. All right, so I integrated the first term, so 3x minus 3 inside every side to 2 over 2. Plus, now if I integrate the second term, it's going to be x minus 2 to 1 over 1 minus x2 over 2 plus c1. Okay, now the question is, can I apply the boundary condition at this stage? Well, you remember when the beam was fixed from the left to the wall, we had a slope, so we had a condition for the slope. So at this stage, I could set something for this v dot, which is a slope, and then find C1. But in this problem here, I don't have any information about the slope of the neutral axis at point A and C, as you can see. I have actually nothing, no information about the slope at any point across the beam. So what should I do? Well, the answer is, I don't have to specify C1 at this stage. I can just go ahead and take one more integral. Okay, so if you take one more integral, let's use a different color for integral, one more integral of both sides of this equation, what do I get? Let's do that. For the left side, you get v, or simply v of x, is equal to, for the right side, you get 3 over 2, that's going to be x minus 3 to the 3 over 3, plus x minus 2 over 2 minus x 3 over 6 plus c1 times x plus c2. Look at that. C1 is just a constant, so when you take integral, it becomes a constant times x, which is c1 times x, and then you gotta get another constant of integration coming from this green integral, the second integral. This method usually called in a structural analysis curriculum is called double integration method, because you have to do two integral in order to get the deflection relation. Okay, so I can easily say that, well, because let's do a little bit simplification. This 3 right here is going to cancel with the 3 right here, so I just erase them, and this is my simplified relation. So now I can apply boundary condition. Why? Because I have information about my deflection. This curve is all about the deflection. So I can specify this curve at point both A and C, which I'm talking about these two conditions right here. Okay? These two conditions. V at x1 is equal to 0. V at x3 is equal to 0. So let's write it here. Relation 1 was V at x is equal to 1 was 0. That means that, let's put x1, let's substitute x1 in this relation and see what we can get. Well, if my x is 1, this term, the first term on the left, let's zoom on it, x is less than 3, so the first term does not exist. The second term also, x is equal to 1, less than 2, so the second term also does not exist. So the only thing that I have is the third and fourth and fifth term from the left. So if I put there x is equal to 1, I get negative 1, 6 plus c1 times 1, which is c1 plus c2 is equal to 0. This is the equation I get when I apply this boundary condition. V at x equal to 1 is equal to 0, or deflection at point A is equal to 0. Now let's apply the second condition. It says V at x is equal to 3 is equal to 0. This is the second condition right here. Equation number 2, highlighted. Need another color for highlighter, maybe pink. Equation number 2. This was equation 1. This one is equation number 2. So I'm using equation number 2 right now. V at x equal to 3 is equal to 0. So let's put 3 in this equation. What do I get? V at x, I'm putting 3 in this equation. Okay? V at x equal to 3 is equal to, the first term is 0, obviously. The second term, if you put x3 become heavy side, 3 minus 2. Well, because 3 is greater than 2, this simply heavy side become parentheses. 3 minus 2. to the second power divided by 2. And what is that? That is simply 1 over 2, or half. So simply, here, I just simply put 1/2. Okay? So I get 1 over 2. And then the next term, x is 3. So 3 to 3, which is 27 divided by 6, plus C1 times 3, 3 C1, plus C2 right here is equal to 0. That's my second equation. That's my second equation. Well, you can just go ahead and at this point we're done because you have two equations. Let's put a circle around, box around them. This equation 1 and equation 2. How many equations do I have? 2. How many unknowns? 2. Highlight them. C1, C2. C1, C2. 2 equations, 2 unknown. Once you solve these 2 equations for C1 and C2, then you get 2 constant of integration. So that means you get your deflection of neutral axis very, very accurately. So let's do that. Here, let's do a little bit of simplification. So here, this term, you're gonna get 1 over 2 minus 27 divided by 6. And here you can just simply say, well, this is 3 times 3 times 3 divided by 6. This goes with this, so you have 3 times 3 divided by 2. So the entire thing is half minus 9 over 2, which is equal to negative 8 over 2, which is equal to negative 4. Okay? So this entire thing is just simply negative 4. So let's erase this extra information here. Yeah, this is acting very slowly, this iPad. I don't know why it's not erasing it. Yeah, it should. Okay, alright. So this thing is just simply negative 4. So let's put these equations together. The first equation is C1 plus C2 is equal to 1 over 6. The second equation is 3C1 plus C2 is equal to 4. Now we want to solve it. There are gazillion different way of doing this to get C1 and C2. The way I can do it is simply using method of Gaussian elimination. Multiply the first equation by negative 1 and then add it to the second equation. If you do that, then we simply get, let's multiply the first equation by negative 1. So you get, the first equation become negative C1 negative C2 is equal to negative 1 over 6, and then the second equation is untouched. 3C1 plus C2 is equal to 4. Now add them together. You get 3C1 minus C1, 2C1. C2 cancel out, and then you get 4 minus 1, 6, which you can simply write 4 minus 1, 6, and 6 goes to the bottom. 24 minus 1, which is 23 over 6. So then that means your C1 is equal to 23 over 12. And then you can substitute in this relation, equation number either 1 or 2, to get your C2. Alright? For example, if I substitute here in this equation, then I get 3 times C1, 23 over 12, plus C2 is equal to 4. Here, 12 over, this becomes 23 over 4, plus C2 is equal to 4, and that means C2 is equal to 4 minus 23 over 4. Once you get C1 and C2, what is your deflection? Your deflection is V of x. Let's write it here, V of x, deflection at any x. I'm just simply rewriting this equation. Let's highlight it. A better highlighter. This equation that I obtained before, the only thing I needed to know was C1 and C2. Now I got C1 and C2, all I need to do is to plug it back into the equation and get the equation of the deflected neutral axis. So V of x is equal to 1/2 of x minus 3 to the 3 plus 1/2 of x minus 2 to 1/6 x3 plus C1, which is 23 over 12 x plus C2, which is simply plus 4 minus 23 over 4. This is a relation that you can plot it and get this deflected curve, which is a complicated curve, like for example here. It's a complicated curve. I recommend you guys to plot it using either hand plotting techniques or just use a computer program to plot it. Now, next thing I want to discuss is the buckling. So I'm going to put that topic in the next video, the concept of buckling. And for example, if you have a beam, a column, actual, it is a column, under some load, then what we discussed in the axial load section, this thing is going to compress like that. And we also talked about Hooke's law. The normal stress is equal to E epsilon, and well, we could say it is equal to F over E delta L over L, and then you can simply write F is equal to E over L delta L. So this is going to act like a spring because force is proportional to the deflection, and this is agreeing with the physics, because I know that if I apply a little bit force to this column, it's going to go under some compression like that. But you can see if this column is slender like that, so the diameter is small, the ratio of length to diameter is simply too big, then there is another possibility. That means if I apply a load to the end, it may compress like that, or it may simply buckle, right? So it may buckle or it may compress. So that's the topic of the next lecture. I'm going to show you the equation, and we are going to do some application how to do buckling computation. All right.